I will begin with a word of prayer. Sorry about the audio today. I don't have a mic, so it's going to be a little bit, well, like everybody else's videos, I guess. But anyway. Dear Father, we thank you for today, and thank you for your students. Just ask you to bless our work today, Lord. In your name I pray, Lord Jesus. Amen. So here's the say independent sheet, lest I forget. So we started talking about isomorphism, right? So we should talk about that some more. What was an isomorphism? If we have psi, a mapping from V to W, both V and W vector spaces over a field, right? And psi is a linear bijection. And psi is an isomorphism. And we say V is isomorphic to W. So isomorphisms are, of course, important, and we'd like to understand them and how to build them and analyze them and so forth. So one of the first things I might notice is if we take, suppose we had a few of them, right? Like, theorem. If we had psi 1 that said, that one go from, say, V1 to V2, and psi 2, let's say it goes from V2 to V3, then psi 2, composed with psi 1, is a mapping from where to where? From V1 to V2 to V3, right? Because the first one goes first and the second one goes second. Sometimes I draw a picture like this just to try to make sure I'm not, deceiving myself in terms of the composition, right? Does that make sense? At least the composition is an isomorphism, provided that psi 1 and psi 2 are isomorphisms. All right. The inverse of an isomorphism is also an isomorphism. So to prove this little theorem, there's not much to do if we already have our ducks in a row. So the proof goes like this. Let's just outline the proof at least. Number one, psi 1 linear map from V1 to V2, right? And psi 2, a linear map from V2 to V3, implies that the composite of 2 and 1 is a linear map from where? From V1 to V3. Because we proved in last class that the composite of linear transformations is a linear transformation, right? And then number 2, the composite composition of injective maps is injective, and the composition of surjective maps is surjective in this context at least. I mean, we could give a more detailed proof, you could look at another way we could do number 2, just to be more linear algebraic in the argumentation. What would the kernel we could look at like the kernel of the composite, and we could argue that that kernel had to be just containing 0 as a result of the kernel of psi 1 and psi 2 just being 0. Anyway, so this is just a sketch, but you can prove that the composition of isomorphisms is an isomorphism. And likewise, you notice that I say a linear bijection? That's enough. That automatically gives us that, what? If it's a linear bijection, then by our previous theorem, we know that psi inverse is also linear and bijective, right? And that's why I'm correct to say that the inverse of an isomorphism is also an isomorphism. All right, so example 1, let's consider basis like 1x, x squared, x cubed for P3 of reals, right? And I'll consider basis gamma equal to, let's say, we use the other notation, E11, E12, E21, E22 for R 2 by 2. All right. Now I wanted to show you guys, it's good for you to read the notes, of course, and to understand the proof of the existence of the unique extension theorem, but it's probably even better for me to use the unique extension theorem to build a map to talk about this. So here's 2 bases, right? We have a basis for P3, and we have a basis for gamma, right? I want to build an isomorphism from one to the other. Here's one of the ways I can do it. I can say, oh, okay, well, I'm going to say that, I don't want to say, sorry, I'll choose a letter eventually here. Psi of 1 is E11. Psi of x is E12. Psi of x squared is E21. Psi of x cubed is E22. So let me say construct psi by defining this, then extend linearly. So my argument is that we can prove that if we map a basis to a basis, all right, then it's necessarily the case that a map constructed in this way must be an isomorphism. Right? Extend linearly. What do we mean by that? Well, let me make it explicit. I mean specifically that psi of a plus bx plus cx squared plus dx cubed is a times psi of 1 plus b times psi of x plus c times psi of x squared plus d times psi of x cubed, which is explicitly ae11 plus be12 plus ce21 plus de22, which if we write that explicitly is a, b, c, d. I defined the map that I've explained in the black at the bottom of the board using the blue language, though, you see. I do have a choice. I can define maps simply by ascribing where the basis goes to, and then say extend linearly. If you tell me where the basis goes, that fixes the action of the map on the rest of the vector space. Now, why is this an isomorphism? Can we argue? What are some reasons that you could think of? How would you prove that psi is an isomorphism? Supposing we don't already have the theorem that if we have a map that maps a basis of one vector space to a basis of another vector space, that's an isomorphism, right? Setting aside that theorem, from which it's immediately true that this is an isomorphism, suppose you don't know that, right? How would you prove that psi is an isomorphism? Let me start you out. Point number one, psi is linear by construction. That's the beauty in part of the linear extension theorem, is that when we use the linear extension theorem, we're not obligated to prove linearity because we already have it from the theorem, logically. So like I prove linearity once and for all by proving that theorem, and then I don't have to if I use this technique. So that's nice. Why is this one-to-one? How about this? We had noticed that the span of beta is what? P3R, right? And oh, see, this isn't quite the theorem we had, is it? We had a theorem that said what? If you have a spanning set and you feed it to a surjection, you get a spanning set for the codomain. In this problem, we know, I would argue, that gamma and beta are both bases for their respective vector spaces, right? But I'm trying to prove the surjectivity of the map, you know? I don't know, I mean, I think, let's not try to be like super clever or anything here. How would you prove that this map is onto? I think it's not that complicated, is it? Let A, B, C, D be an element of R 2 by 2, right? Then psi of what is equal to A, B, C, D? See if you can fill in the blank. You have just proved it's a surjective map, right? This is what it means to prove it's onto. You pick an arbitrary element in the codomain and show that you can map to it from something in the domain. You fill in the blank for me. It's not hard, right? What do you put there? Don't leave me alone with my thoughts. Please. Right? Come on, please. Someone here could have said this. All right, so this maps to that. That's an arbitrary point. Therefore, psi is surjection, right? And then 3, how do we prove it's a injective map? Like, what could we use there? I mean, how about we just calculate the kernel? You know, what's the kernel? If A is in the kernel of psi, right, then psi of A is equal to 0, but that means that psi of A, expanding A, B, C, D is equal to, oh man, I'm sorry guys. What's the input? Duh. Let's call that f(x), yeah. Psi of ax, oh good grief, a plus bx plus cx squared plus dx cubed is equal to a, b, c, d is equal to the 0 matrix, right? What's that mean? That obviously means A equals B equals C equals D equals 0. Therefore, f of x equals to 0 as well, right? I call this thing f of x, just to be clear. Which then tells me the kernel of psi is 0. Therefore, psi injective. It's probably good for us to go through these arguments like this rather than using some theorem at the moment. All right. But I'm just telling you, this has to happen. Anytime we build a map by sending a basis to a basis, it is inescapable that it will be an isomorphism. Perhaps the most important isomorphism, though, is the coordinate map. You see? What's the coordinate map? Let's remind ourselves how that works. So if we've got a finite dimensional vector space, and don't worry, despite the, like I do try to talk at least a little bit here about like infinite dimensional vector spaces, but I really don't have any good problems yet on the infinite dimensional coordinate maps. So you can kind of like read that lightly or not at all, and it won't hurt you. I do want you to understand that we defined dimension, in terms of cardinality. So, read my solution, see what I have to say about that, right? But we will limit the discussion of coordinates in here just to finite dimensions. So, like, if the dimension of V is equal to n, and beta V1 through Vn is basis, right? Then if x in V has x equals to the sum, I equals 1 to n, let's say Ci Vi, then the coordinate vector of x with respect to beta is defined to be, the column vector of these constants, right? And we also have another notation. We also like what's called phi sub beta acting on x, all right? So that was this is the definition of coordinate map. So a theorem we can prove that would be super easy to prove is that phi beta is, it goes from the vector space V to Fn is a linear bijection. I would point out more. I would point out that you could define it by linearly extending, alternative perspective. We define, phi sub beta acting on Vi just to be Ei. For I equals 1, 2, n, then extend linearly. In fact, this is the unique linear extension off this. And I like to put this into words. What does the coordinate map do? Can you guys help me out? Let's put this into words. What is it doing? So the phi beta coordinate map changes the ith abstract basis element to the ith standard basis. That's what it does. How does the inverse work? Like what's phi beta inverse? Well, if you feed phi beta inverse EI, guess what you get? You get VI just the same. It's important to know about this and be able to use it in calculation. All right? It's actually very helpful. So I want to show you a proof that any two vector spaces of the same dimension are isomorphic, all right? Now, one way you could prove that is if you already have the theorem that I've mentioned, but I've mentioned this theorem that if we have a linear map that sends a basis to a basis, it's an isomorphism, right? If you already knew that theorem, then proving that two vector spaces of the same dimension are isomorphic would be an immediate corollary to that theorem pretty much, right? But so let's suppose we don't know that theorem, and we just want to prove that two vector spaces of the same dimension are isomorphic, all right? I want to show you how to prove that using coordinate maps. So here's a theorem. V over F and W over F with the dimension of V equal to N equal to the dimension of W, then V is isomorphic to W. So I want to introduce you to a way of thinking, and it's graphical, I suppose. So what we do is we draw a picture, sort of an abstract picture of V. All right? And I draw a kind of abstract picture of W over there. Right? Now the thing is, they're both connected to Fn. Right? I could draw a picture down here of Fn just the same, you know? And how do I get from V, and let's, without loss of generality, let's say beta V1 through Vn is the basis here, and gamma W1 through Wn is the basis over there, right? So you guys tell me, how do I map from V down to this? Like what mapping goes like from here to here? V1. All right, I'll do it. Beta. Phi beta is the mapping that takes like x up here, right? And trades it for the coordinate vector of x down here. That's how that works. And over here, on the other side, we can trade, you know, this point, say y, under the gamma coordinate map. See, that trades it down here for a vector y sub gamma. That's the coordinate vectors of y. Now I want an isomorphism that goes from here to here, right? Now I've drawn these like they're separate. It's the same set though. What's an isomorphism that goes from one set to itself? Well, I should have told you this about this already, but the identity map does that, right? So the identity map just does that. So this is the identity map on Fn. So I want to go from the left to the right. How should I achieve that? What can I use for my isomorphism? Let me draw a picture. What if we do this? do this. Like that. What is that? Well, the last shall be first in composition. So the last thing I do is go opposite the phi gamma. So I do like phi gamma inverse composed with the identity, which is kind of silly, right? And then the first thing I do, phi beta. So I'm saying psi equals the inverse of the gamma coordinate map composed with the identity composed with phi beta. Now the identity is kind of like, I mean, you could do without that if you wanted. If you just want to make this picture just the same Fn for both spots, that would be fine too, right? So my question to you guys is, why are we done? Why is that an isomorphism? What are we looking at? So I just told you a theorem that the coordinate map, and this would be easy to prove, right, is a linear bijection. Right? You can prove that the coordinate map is linear, and you can prove that the only thing that maps to 0 is the 0 vector, and that it's surjective. It is a linear one-to-one and onto map. It's an isomorphism. The coordinate map is an isomorphism. The inverse to an isomorphism is an isomorphism. Isomorphism. The identity map also isomorphism. So we're looking at the composite of isomorphisms, which is once more an isomorphism. Therefore, we have an isomorphism from V to W, namely this. Because the direction is different. I start here. I'm going with the phi beta, but I'm going opposite the gamma. So I think we can even see this general construction in my first example, maybe. If we think of I may have the beta and the gamma mixed up. I'm not sure about that. But we don't need to do that. But let me. All right, so enough of that. Let's play around a little bit more here. Find another example for you guys. Maybe happen to have the course planner in front of them. I lost track of where I am, guys. I'm trying to make sure I'm not. Because I have this habit of going further into something than I should. What's today? Oh, I better do that then. So let's talk about the matrix of a linear transformation. It is tied to this discussion. So here we go. So here's the definition. Given T, a linear map from V to W such that beta is basis for V and gamma is basis for W, both finite dimensional. Then we can define the matrix of linear transformation as follows. I am a victim of my own printing. All right. My apologies if the definition I'm about to give you is not the definition of the notes, but this could be a definition. So, then T beta gamma. You know what? Let me. This is annoying to not just tell you the dimensions. Let's say that the dimension of V is n, and the dimension of W is m. All right. Then this is an element of F m by n, as in mommy by n, is defined by T and gamma equal to, oh, rats. I need more notation. I'll put the rest of it underneath this equation. T beta gamma. So the first thing we do is we take T of V1 with respect to the gamma coordinate, and then we do T of V2 with respect to the gamma coordinate, T of Vn with respect to the gamma, where beta is V1 okay, so you got to start somewhere. So this is just the definition I wrote today, but you could define it other ways. You can prove theorem is this, that the matrix of T beta gamma, so constructed above, times the coordinate vector of x with respect to the beta basis is equal to the gamma coordinate vector of T of x. Think about it. You can also use this formula to define the matrix of a linear transformation with respect to a pair of bases. And oftentimes I use what I just wrote in blue as a means of calculating it, truth be told. So there's this definition, there's this calculational principle, but there's another way of, the third way of understanding third way of understanding the matrix is if we let left multiplication by A on x to be equal to like AX for any A in, say, Fm by n and x in Fn. So like this is the left multiplication by A map, all right? Then another way you can look at the matrix is like this, diagrammatically. So here's my V, here's my W, with the beta basis, with the gamma basis. T goes from V to W, it's linear. But you see, I can trade a point here, x, for a coordinate vector down here, x beta. And I can, x maps over here to T of x under T, right? And so T of x I can also trade for a coordinate vector down here, T of x. But down here we're talking about, what are these vertical arrows? Same thing that I was talking about in my larger discussion of isomorphism over here. Those are the coordinate maps, treating the abstract vector space V for Fn. So this is like, well, this is phi beta, so this is Fn. This over here is phi gamma, so this is Fm, right? And the matrix of the linear transformation is what you need to go down here, you see. So to get from here to here directly, I do left multiplication by this thing, phi beta gamma. And what I want to say is, oh, come on. I'm sorry. How long has it been? I wonder if I missed an example just now. I'm sorry. My apologies. I did that before I did the isomorphism, right? This is from before I talked about isomorphism, right? Yeah. So hopefully I moved the camera a bit before. But anyway, so this diagram actually tells you everything in terms of how these things work together. So like, you can either go like, let's see here, you can either go like this, or you could go the other way. All right? So the blue, in other words, phi gamma composed with T should be equal to left multiplication by T beta gamma composed with phi beta. So in this way of thinking, we can define an alternate definition for the matrix is that it's left multiplication. I'll get it eventually, guys. Left multiplication by T beta gamma is equal to, you see, phi gamma composed with T composed with phi beta inverse. This is sometimes a very convenient way to look at it. This will be especially important to us as we study coordinate change, probably next class. But we need to set this up and at least start with, right? Now, obvious question is, if you really understand this, we ought to be able to prove, we ought to be able to get from one of these ideas to another, right? Can we do that? Can we show that if we know the diagrammatic one is true, does the other one hold true? Right. Let's see if we can do that. So suppose suppose we know left multiplication by T beta gamma is equal to phi gamma composed with T composed with phi beta inverse, all right? So let us, assume this. I think if we do this right, this calculation is going to be reversible though. All right? Multiply both sides. Well, rather, let both sides act on the ith standard basis element. What does that tell me? So L of T beta gamma acting on EI is just, what that means is T beta gamma times EI, which is column I of the matrix, right? That's what it means. If we multiply a matrix by the ith standard basis, it picks off the ith column. We know this, right? But on the flip side, this is equal to phi gamma, right, of T of phi beta inverse of EI. But what is, by the way, phi beta inverse of EI. What did we say about this? I just erased it, but it was here before I erased it. What was it? Remember? Phi beta is the map that takes VI, the element of the basis beta, and maps it to EI. The inverse undoes that. So this is by definition VI, which makes this phi gamma of T of VI. But hey, that is nothing more than T of VI gamma. But what did we write in my initial definition? Remember what we wrote? We wrote T of V1 gamma, T of Vn gamma, right? So my point to you is that actually it's pretty clear that if you start with the top thing, it implies this, which implies that. But in fact, these calculations are reversible. If you know this, it implies the step above, which actually then, when you sort through it, implies the step above. So these are actually three equivalent formulations of what it means to define the matrix of a linear transformation. So when you're calculating the matrix of a linear transformation, you have all of these to choose from. I personally prefer this one. Let me show you. So like example 2 here. Suppose we have like T of f of x is equal to, say, f of 0, f prime of 0, plus f of 0, f prime of 0, and I'll put an f of 0 here again. All right. And we want to make T go from where to where? Let's do P2, yeah? And its output apparently is R2 by 2. So we need a basis for the domain and a basis for the codomain to calculate the matrix, right? So how about this? We'll use basis 1x squared for that guy, right? And we're going to use the basis, this is the so-called lexicographically ordered 1, 1, 1, 2, 2, 1, 2, 2. This is the lexicographically ordered basis for the 2 by 2 matrices, right? All right, so here's what I do, guys. I start out with my arbitrary element, which would be most naturally a plus bx plus cx squared. Do you see why I do that? And I'm going to call that v because it's nice to call it v. Then I map this under my given transformation over here to T of v. Can you guys help me out with that? What is that? We'll start out small. What's f of 0? Maybe I should have called it f instead of v. My own stupid fault. Now let me call this f of x so it's less weird. Just a, all right. And how about f prime of 0 plus f of 0 is what? That's b plus a, right? F prime prime of 0 is, what's f prime prime of x? It's 2c, right? So we got a 2c down here, you see. F of 0, well that's a again. So here's my T of f of x, yeah? Great. Now what I do is I look down here at what's my coordinate vector with respect to the beta basis, right? And I look down over here and I say, well, what's my coordinate vector with respect to the gamma basis for that output for T of f of x? Now we have to mind the bases, right? So I put 1, then x squared, so that I did that because I wanted this to end up being ABC. All right? The coordinate vector of f of x is ABC with respect to the monomial basis in the ordering that I have. What's the coordinate vector for this? Well, I did E11, so I put an A here, B plus A next, 2C, and A. Now, those could have easily been shuffled around if I had ordered the elements of gamma differently, right? It was gamma in my heart, it's not on the board. So, then, to get from here to here, we multiply by T beta gamma equal to what? And I usually write it out. One more step I usually write out to help myself out, which is I like to do a kind of fill in the blank kind of deal. So like I'm looking, so we're going from 3 dimensions to 4 dimensions, so we're looking for a 4 by 3 matrix. So 4 rows, 3 columns. We want it to multiply ABC and to pop out this A, B plus A2C and A. Really? Well, I'll not get back in a second. I'm kind of happy she rickrolled you guys, but anyway, I'll take it. So then you just fill in the matrix, right? It's 1, 0, 0, 1, 1, 0, 0, 0, 2, 1, 0, 0. There you go. We've found our first matrix of an abstract linear transformation. This is how you do it. When I used to teach this class to lots and lots of elementary like math major people were going to teach like, you know, arithmetic to kindergartners, those folks, they don't want to be here, right? They really don't want to be here. But they could do this. You can do this. It's not that bad. You'll get used to it. It's really harmless. This is a fun calculation. And I think most of your next homework is one way or another about this. So I hope that helps you get started. But anyway, I'll stop here as I must call the home base.